Hi everyone, it's a pleasure to participate in this relevant conference. My name is Listes Araújo. I am professor at Federal Center of Technological Education of Minas Gerais. Now I am going to present a practical deconvolution approach to obtain lightning electric fields profiles, preliminary results. Here you can see the outline of my presentation. First of all, I'm going to make a brief introduction to present the context of the work. Then I will present the main features of the electric field measurement system. In sequence, typical electrical field change profile of negative downward lightning measured. After approached methodology, after preliminary results, including laboratory tests and real events of lightning discharges. At the end, I will proceed with the conclusions. So let's begin with the introduction. The measurement of lightning electric field profile is an important and well-established parameter for assessing the lightning process. Traditional measurement systems of electric field lightning events use antenna or plate antennas. However, such systems deliver electric field records that vary based on the decay time constant of the antenna system. The electric field waveform must be processed in order to obtain the actual electric field profile, so that the slower variations, such as long continuous current, can be observed. The main objective of this work is to present and discuss the developments of a practical approach to obtain the compensated or the convoluted vertical electric field from raw electric field data obtained at Federal Center for Technological Education of Minas Gerais, which is located in Brazil. Now, I am going to present the main features of the measurement system installed at CFET-MG. Here in this figure, you can see the main components of this system, which are flat plate antenna, analog integrator, and digitizer. The left side of this figure, you can see the real flat plate antenna installed with a solar panel. The time constant of this IFS system is 0.6 milliseconds. The right side we have a digitized, which are composed by PXI and PCI boards. In order to have a time synchronization in our measurement, a GPS receiver is connected to the data logger. This figure shows a typical profile of electric field changes of a negative downward lightning flash obtained with measurement system illustrated previously. Note, these pulses here indicate fast electric field changes associated with return stroke currents. After the last pulse here, you can see a small offset component which is related with the continuous current of downward lightning. In this paper, the atmospheric cycling convention will be used when referring to the electric field and its change. I mean, strokes that transfer negative charge to ground are considered negative strokes. Now, I am going to present the methodology of this work. We can see a flow chart. It represents two main blocks. The first one is acquisition system here. The second one is the convolution process. Basically, the electric field of lightning feeds measurement system, and the result is the well-known electric field change profiles. The deconvolution process consisted of obtaining electric field profile from electric field changes by means of signal processing. The signal processing procedure is composed of several steps. First, the transfer function of the measurement system, shown in equation 1, is analytically obtained in Laplace domain, considering all the features of the integrated circuit. The parameters CCX represent constants of a continuous time system. The second step is to convert a continuous time dynamic system to a discrete time system by means of a function C2D available on MATLAB. As input, it requires the sampling rate of digitized, which is 5 megasamples per second for all data measured by system installed at Cepheid MG. Therefore, we obtained the discrete time transfer function and its discrete time constants CDX, which are shown in equation 2. The third step is to validate the obtained expression. It can be performed by using the step function available in MATLAB. It is expected that both the continuous time and discrete time transfer function reproduce the same result when a step function is applied, since they represent the same system. This figure here shows the step response for both. Note that the curves follows the same trend. In addition, it is noted that the time constant obtained from the transfer functions is quite similar to that of real system installed at Cepheid, whose value is 0.6 milliseconds. Finally, the fourth step, the function has been evaluated. The system can be described by difference equation. The compensated electric field A is obtained by applying expression 4, considering the measured voltage UA. Applying the proposed methodology on real events, the process was validated by means of laboratory tests. For this purpose, the setup illustrated in this figure was built. The function generator was set to apply a square wave signal of 20 Hz between the flat plate antenna and metallic flat plate. The voltage signal measured by the antenna feed the analog integrator and amplifier, which is sampled at rate of 5 megasamples per second. Here you can see in this figure the results obtained during these tests. The black curve shows the electric field changes coded by digitizer. The function generator injected an electric field with a frequency of 20 Hz, which can be seen as a dashed red curve. The blue waveform shows the deconvolution results, which is the waveform obtained by applying difference equation to the data recorded by the digitizer. It is noted that the blue and dashed red curves are quite similar. These data show that the signal processing recovered completely the profile of electric field. Now I am going to present the measurement obtained at Cepheid MG. The proposed methodology was applied to all measured raw electric fields, since the deconvolution process is a very fast task. Among the records, results of 3 negative downward lightning events are shown. For all the events, the blue curves are electric field changes and red curves are compensated electric fields. In this first event shown in this figure corresponds to a lightning discharge of a 4-stroke flash with a long continuous current following the fourth stroke, as you can see here. The compensated electric field profile obtained by applying the proposed methodology resembles the typical waveforms reported in the literature. The continuous current has a duration of approximately 120 milliseconds, indicating that it transferred a substantial amount of charge to ground. The second event is present in this figure. It shows the compensated electric field waveform of multiple stroke flashes with 3 long continuous currents. You can see the first here, the second here, and the third here. As discussed for the first event, the electric field has profiles quite similar to those previously reported in the literature. This figure shows the third event. This event corresponds to a lightning discharge of a multiple stroke flash with a long continuous current, as you can see here, whose duration was approximately 100 millisecond. Now I am going to present the final remarks. It was developed a practical approach to compensate the time decay caused by the system response and regain the original lightning electric field waveforms. The proposed methodology is based on signal processing composed of several steps using MATLAB. The authors believe that the procedure applied on the data of this paper can be used in different measurement systems, not only the setup installed at Cefet MG. Laboratory tests were performed to validate the proposed methodology. Different electric field profiles were applied by means of a function generator, and algorithm was able to regain original electric field profile from electric field changes recorded by digitizer. Several electric field change profiles of real lightning events were recorded by system installed at CFET-MG. All of them were processed and deconvoluted. It is important to point out that the proposed methodology was able to obtain relevant information from raw EFS measurements with very small amplitude. The authors intended to install another measurement system of electrical field change at CFET-MG with decay time constant higher than one used by the EFS field. Determination of strokes from E-field will be verified by high-speed cameras and light location system. Thank you very much.